What if the reason we have never found intelligent life out there is not that the universe is empty, but that we are the rare exception? On November 4, 2013, NASA's Kepler mission delivered a number that felt almost too generous. Roughly 40 billion Earth-sized planets sitting inside the habitable zones of sun-like stars and red dwarfs across the Milky Way alone. 40 billion chances. By that count, the galaxy should be overflowing with life. And yet silence, no signals, no visitors, no signs. This is the core tension of the Fermi Paradox, and one of the most serious attempts to resolve it does not look outward. It looks inward, at everything that had to go exactly right here, on this one unremarkable dot. In the year 2000, geologist Peter Ward and astronomer Donald Brownlee, both from the University of Washington, published a book called Rare Earth. Their argument was straightforward but unsettling. Complex life did not just need a planet in a habitable zone. It needed a very specific planet, built in a very specific way, by a chain of events so improbable that it might have happened only once, or close to it. Let us start with something we almost never think about. The Moon. Earth's axial tilt, the angle at which our planet leans as it orbits the Sun, determines the seasons. Too much variation in that tilt and climates collapse. Ice ages become permanent, or equatorial regions bake beyond recovery. What keeps Earth's tilt remarkably stable over millions of years is the gravitational influence of the Moon. A large moon acting as a kind of gyroscopic anchor, preventing our planet from wobbling chaotically. But here is what makes this even more striking. The Moon was not quietly assembled somewhere nearby. It was born from catastrophe. About 4.5 billion years ago, a Mars-sized body called Theia struck the proto-Earth in a collision so violent it melted both worlds. Debris was ejected into orbit, and from that debris, the Moon coalesced. We know this because the Moon and Earth share nearly identical isotope ratios for oxygen, chromium, silicon, and tungsten. They are made of the same stuff. They are, in a real sense, siblings born from the same wound. The probability of a collision like that producing a moon of exactly the right size, in exactly the right orbit, is not something you can engineer. It happened. And because it happened, we got stable seasons, a regulated climate, and eventually us. Now let us talk about the ground beneath your feet. Plate tectonics, the slow grinding movement of Earth's crustal plates, does something remarkable on timescales that dwarf human history. It acts as a planetary thermostat. Volcanoes release carbon dioxide into the atmosphere. Rainfall pulls that carbon dioxide back down and weathers it into rock. Subduction zones then drag that carbon-bearing rock deep into the mantle, locking it away for millions of years before it cycles back. The result is a self-correcting system that has kept Earth's surface temperature within a range capable of sustaining liquid water for billions of years. Without plate tectonics, carbon dioxide builds up or gets permanently stripped, and the surface temperature trends toward extremes it cannot recover from. The margin is not forgiving. Research shows that a 5% decrease in Earth's orbital radius would push us into a Venus-like greenhouse state. A 15% increase would lock us in ice, like Mars. But here is where the rare Earth story gets more complicated, not simpler. Research from the University of Rochester found that plate tectonics was not actually operating 3.9 billion years ago when life first appeared on Earth. Instead, the planet was releasing heat through what geologists call a stagnant lid regime, essentially a single unbroken crust without the mobile plate system we have today. Life did not wait for the thermostat to be installed. It arrived before the house was finished. This does not dismantle the rare Earth argument, it refines it. Plate tectonics may not be required for life to begin, but sustaining complex life over billions of years, long enough for intelligence to emerge, that is where the thermostat becomes critical. Then there is Jupiter. The classical version of the rare Earth story cast Jupiter as Earth's guardian, a giant planet positioned far enough out to act as a gravitational vacuum cleaner, absorbing comets and asteroids that would otherwise bombard the inner solar system. Objects roughly 10 meters in diameter impact Jupiter somewhere between 12 and 45 times per year. The same size objects hit Earth only once every 6 to 15 years. The numbers look protective, But 2024 simulations complicated this picture considerably. Jupiter's gravity does reduce long-period comet threats from the outer solar system. At the same time, it can deflect asteroids and short-period comets inward, increasing the chance they find Earth. Jupiter is not simply a shield, it is a gravitational redirector, and its net effect on Earth's impact risk depends on geometry, timing, and the specific population of objects involved. The story is messier than the textbook version. And that messiness is important because it reminds us that we are not just looking for planets with a Jupiter analog. We are looking for a Jupiter analog in exactly the right configuration, at exactly the right distance, doing a very precise gravitational balancing act. Add all of this together and the numbers become sobering. Estimates suggest about 20% of Sun-like stars host an Earth-sized planet in the habitable zone. That still sounds abundant. But recent analysis of exoplanet candidates found that only 0.6% satisfy comprehensive habitability criteria, even under relaxed assessment standards. Strip out the systems without a stabilizing moon, without long-term geological carbon cycling, without a favorable giant planet configuration, and that number almost certainly falls further. This is where the rare Earth hypothesis lands its hardest punch. The silence of the universe is not evidence that life is impossible. It may be evidence that the specific checklist required for complex, communicating, spacefaring life is so long and so demanding that most planets get some items but not all. You can have the right distance from your star but the wrong moon. You can have the right moon but a Jupiter that throws rocks at you instead of catching them. You can have stable tectonics but start your life just as a rogue impactor sterilizes the surface. Earth passed every test, not through design, but through a sequence of accidents, collisions, and coincidences playing out across billions of years. So here is the question that stays with you after you sit with all of this. If Earth is genuinely rare, not just in having life, but in having the specific conditions that allowed life to persist long enough to become complex, then what does that make us? Not special in a comforting way, special in a sobering way. The universe did not build us. It built a place where the right catastrophes happened in the right order, and we are what emerged from the wreckage. Is that reason for wonder, or for something closer to vertigo? If you enjoyed this video, consider subscribing to the channel.